computer. It takes a little time here. So let me tell you some things about the project. I showed him to Tomer a basic version. I assume that you know to program with an object-oriented language, isn't it?
Yeah, I know how.
Okay.
I think I know how.
Mm-hmm.
By the way, you don't have any preferred language, right?
Sorry, what?
You
what
don't.
is...
It doesn't need to be in a specific language. We can choose which language.
No, I have this problem. Just a minute. I'm sorry. Okay. Maybe now it will be okay. Yes. Okay. Okay. And before we are going over elliptic curves, which will be the last algorithm we're going to see, I want to tell you something about something further about about field extensions. I mean, you start with a prime field and you extend it by roots of some irreducible polynomial. Okay, so in this case, this extended field contains element of this form, which means that there is a basis which is 1 and x. What is this x? That such that I didn't write it, equals to 0, of course. Okay. So once we have this condition, then any elements look like this. And even if we multiply such an element with another such, then we cannot exceed the degree of 1, because once we get to x squared, we interchange it to -1 minus x. Okay? So all elements are in this way. And so last time I told that you can describe the operation inside this field using some operator overloading in programming, but you can do another thing. Okay. This is only continuous. I would say given a prime field FP extended to L by taking some irreducible polynomial with U. One can describe the operation inside the multiplicative group, which is L star, which is L without zero. Okay, this is the multiplicative group using a matrix realization over the base field. What do I mean? For example, we have KF3, and we look at the extended field. I remind you that the motivation to talk about extended field is to avoid attacks like a numbers sieve. I mean, we have more elements, so the cryptography is stronger, but there is not the arithmetic of the field of the usual one. Okay, so this is better. So we take this extension. This is the simplest one. It's like
what do you have?
Yes.
What is the symbol you write here over
L.
the base field?
Where?
The other one.
UK. This is F. This is nice F. This is field.
This is K. K is first to F3.
K is the prime field of three elements.
Okay.
Okay. When I say FP in general, this is a ZP together with plus modulo P and multiplication modulo P. So this is a field. Okay. P is a prime. Why is it a field? Because if we remove, I mean, of course, any Zn is an abelic group, even a cyclic one. But if n is p is a prime, okay, and you remove the zero, this is the definition of a field. That if you take the ring and you remove the zero, you get also, with respect to the multiplication, an abelian group. And here, UP, the Euler group, will be indeed, will contain all elements. I mean, once you remove the zero, all elements belong to the, are invertible modulo P, because all numbers are prime to P. So this is the basic prime field, but we can extend it. For example, this field contains elements of A plus XB such that x squared is -1. It's just it is just like writing I. Okay, the same thing. And so this field L contains 3 square elements, because you have A and B. Each one can be anything from F3. Now, instead of writing by operator overloading the multiplication between two such elements, you can, okay, look at the action of the basic element of L over K. This action on L elements. So we take, I mean, remember this X is just I. Okay, this X is actually I. Okay, we call it I. Okay, so what is the action of I on a general element? I mean, first take the first basic element. The first basic element is 1. So how does 1 act on A plus IB? It's just by multiplication, the regular one. So it stays, it remains A plus IB. But when you multiply I with A plus IB, you get IA minus B. So if we want to translate these elements into vectors over F3, not, I mean over K, so then this will be, the description will be A psic B, and A psic B remains A psic B under 1. But A psic B under the action of I, if the first element represents the element without the X, okay, so now after the action it will be minus B, and this B will be A. So you can represent, okay, so we present A plus IB using 2-on-2 matrix over K. Okay, so A plus IB. Now I put on the rows of the representation the product of the basic element action, which is AB minus BA. Okay, so this is in L star, and this is in GL2 K. Of course, this is not all GL2. Okay, this is only an embedding. For example, now if you take, instead of writing A plus IB, multiply C plus ID, which is AC minus BD plus I, which is BC plus AD. You can do the same thing using the matrix realization. I mean, and now this is the normal multiplication, because it is just represented in GL. So AC minus BD, you see this is this one. Okay, this is the element E always represents the element without the E, without the I. And now we will have AD plus BC. And the same thing here. We will have here minus BC minus AD. Let's do it in some green. Okay. AC minus BD. Okay. So instead of writing some operator overloading, you can just translate any element in the extended field to an element, to a matrix element, and the computer knows how to multiply matrices.
Question. So the first row is obtained by multiplying these matrices by 1, and the second row is obtained by multiplying these matrices by I.
Not the matrix, the rows. You see?
Yeah, but yeah, exactly. So here in the example, you showed us only the example of 1 times A plus IB times C plus ID.
Yes.
You didn't show us the example of I times A plus IB times C plus ID, right? So this will be
no. These are belong to K. I mean, this was motivation. The motivation was to not using any element of. I mean, this represent an element here. This.
I understand. Where is the second line at the obtained matrix at the end? You have an expression at the bottom, right? But you don't have a corresponding expression. You didn't show us a corresponding expression here, right?
No, why? This is this. Of course. Okay.
So you always get this kind of. I'm not sure it's called antisymmetric matrix, or it's something like that.
No. This is called Weyl restriction of scalars. I mean, you just represent the extending field using a matrix from a lower field, okay? And once you embedded your group inside GL, so it becomes just the multiplication of matrices. This is the idea. Okay, so this may avoid using some operator overloading. Okay, now the main thing.
Question?
Yes.
Why did you choose 1 and I? Why not 2I or 3I?
The same. Like you could. I mean, it's not the only way to represent. I agree.
But the minimum is to go over all the bases, right? Because
yes.
1 is not enough.
No, yes, of course. I mean, you could take another base. Yes, of course.
So I can think about the dimension as like 2 vectors, or that
yes,
I need.
But if you tell me that, I want to give you. I mean, we since we concern about we concern extensions of a finite field, and a finite field is always perfect. And why do I mean perfect? I mean that any extension, any algebraic extension, okay, is separable, which means that you have n distinct roots. So you can just take the roots for the basic, for your basis. Okay. So I would okay. So we don't have to be worried about extension which are not separable. Okay. Okay. So what I want to do is to show you the elliptic curves cryptography, and maybe we finish it if not today, next week. And then I want to present to you the project. And then once you finish it, okay, of course there will be some deadline. We're going to meet similarly, I mean in Zoom, and you will send me and Tomer the code and maybe some answers, and then we meet and we talk about it. And so this will be our last meeting. Okay. So let me talk to you about the elliptic curves.
This one is the last one, or we have another one next week?
No, we have next week a last one, and the very last one will be the presentation of the project.
Yes,
So
okay.
So 2 weeks from now, which is not yet the end of the semester, we don't have a lecture, right?
Yes.
Okay.
Instead of the last semester, we will meet, I don't know, in a month from now, I don't know. And this will be the presentation. Okay. Okay, so let me talk. Let me talk to you about the projective plan. Maybe you have heard about it. I mean, more generally, the projective space. You know that in our view, in our eyes, I mean, if we have looked in only one eye, there is no way that we can capture the distance of objects in the space, because we look at lines that come out from our eye, and from this point of view, if there are two objects in the same angle, okay, so maybe we can, because of the size, may think that one is near, but normally we don't have any way, okay, to understand what is the distance. I mean, the two eyes.
It can be, as an example, I can help you with an example.
Mhm.
If you are at the shore by the sea and you look at the ships, some ships will look very big while others very small, but it's an illusion. That's
Mhm.
just because they are closer. It doesn't mean that they're actually bigger.
So thank you. So this is actually, I mean, there is all mathematics. If you in algebraic, okay, they more concerned about projective space from a affine space, because this contains only also the infinity, the point in infinity. I mean, when we look, I mean, we see, for us the infinity is the finite of what we see. Okay, so okay, I will a little right now. What is the projective space? So let me draw something here.
Is it projective space or plane?
A plane, it's a particular case.
Yeah, okay, okay.
This is the Euclidean R3 space. Now, suppose we have a sphere here. Okay. No, this is not really what I want. I need to. Okay. Okay. So this is kind of a sphere. And we look at this point. This point is 0, 0, 1. Now, I'm sitting here and I'm watching the whole plane of XY. And there is a correspondence between elements in XY. For example, this element here, this point here, and a line or a vector that goes from me to this point. Okay. Now, when I say correspondence, of course, any point here corresponds to a single line. So actually, this sphere corresponds to the plane. But there is one point over this sphere which does not correspond to any element here, which is the pole. I mean, if you look at vectors that parallel to XY, you don't reach any element of XY. Okay, so Okay, let me write a little. Okay, let 0, 0, 1 be called a pole. Okay. Any point over the XY plane corresponds to a line or to a single line that starts, or I would say that goes through this point and the pole.
So the point is above the XY plane or on the XY plane? Because you wrote over.
No, it goes through. It
So
goes
it-
through the plane.
So it, okay, so, okay,
It makes a hole here.
yeah. So I can think of it as a Karen, a ray.
Yes, exact. How do you say it in English? A corner?
I
don't
think
know.
ray, I think.
They?
Ray,
Rain.
ray, R-A-Y,
Ray. Yes, Ray.
I think.
Yes, this is right. This is Ray. I searched for this word. Okay. Now, instead of talking about lines, or I would say rays starting from the pole, we can refer to the vector of this ray. Okay. This vector direction does not change when or by multiplying by a scalar. Okay. So, but there is one vector that does not, however, represent such a ray, which is 0, 0, 0. I mean, 0, 0, 0 has no direction, okay? So now we can define our projective plan. Is, I mean, projective plan over R, because you have the same thing over different fields. This is how you write it. RP2. RP2 is actually taking all vectors, three-dimensional. You remove the 0, which is not a vector with a direction, and you divide it. I mean, it's modulo all vectors I mean, by dividing in this way, I identify, okay, for example, one, we write it, usually you write it in this way. Okay, it's the same as, I mean, when you do this quotient, you mean I identify all directions that differ only by a scalar multiplication. For me, it's the same element. So this is how we write elements in the projective plan. I mean, the only thing we care about, and this is how we see, how we look. The only thing that we care about is the angle. That's all. Okay. I mean, we don't really capture space and Euclidean space. We just capture angles. Do you see what I mean? I mean, we are not able to see. I mean, if something, I mean, is in one angle, so we can see something other in the same angle. So we just see angles. We don't see really the space. This is called the projective plan. Okay. Now, okay. Now another definition is of homogeneous polynomial. Maybe you have heard about it. An homogeneous polynomial is a polynomial in some variable. It doesn't matter how many. Such that any total, any monom, I mean, polynom is as some monom, any monom as the same, I mean, all monoms as the same or have the same total power of variables, powers of total sum. Example. Okay. For example, P of x, y, z, x squared plus txy plus y squared plus yz, okay? You see all total powers of variables is 2, 2, 2, 2, and 2. Okay, is a homogeneous polynomial of order 2. But and P, say pxy, I don't know. Is a polynomial, is a homogeneous polynomial in two variables of order 4. You see, total powers is always 4. Okay, and the property of homogeneous polynomial of order, I would say k, is that if you put if you put in the if you put in your input some scalar multiplied with your vector of variables, okay, if order k, so you can move out, take out the scalar in a power of k of px. Because every time you multiply this lambda, okay, so it is I mean, what is for example, what is lambda x, y, z? It's just lambda x, lambda y, lambda z. So if p is like we said before, then p lambda is like taking out, because it's of order 2. I mean, lambda 2 is here, lambda 2 is here, lambda 2 is here. Okay. Over the projective plane, this is good, okay? Because for us, lambda x is x. Because these are the same, lambda x and x. So in in the world of a projective space, okay, it's the same thing. Okay, because anyway, lambda is going out. I mean, because for us, a vector multiplied with scalar is the same like the vector. Okay. Now, why do I show you all this? Why do I show you all this? Because we want to talk about an elliptic curve. Definition. Okay. A smooth mean that everywhere you can put a tangent space. Okay, a tangent space of a curve is a line. I mean, at any point, it's of course another tangent line, and the tangent space of a surface is a plane. Of course, in any point, it's another plane, but it is smooth. I mean, smooth. You don't have singularities. Okay, so a smooth elliptic curve by the way, why do I wrote this? Because if we only care about the solution of a system of polynomials, I mean, if we have what we call variety or manifold that is defined as the 0 points of some system of polynomials, then if it's homogeneous, it will be the same 0 space for x and for lambda x, because I mean the 0 of this is exactly the 0 of this. Okay, it's the same zeros. Okay, a smooth elliptic.
What do you mean?
Sorry?
The same zeros. What do you mean exactly?
I mean, how do you define a variety? So you take some
what?
system
A
of,
variety?
yes.
Okay.
You take a system. I mean, if it's an algebraic variety, so it's defined as a 0 space of some polynomials. So you have P1 is 0 and P2 is 0, for example. Now, if these polynomials are homogeneous, okay, so you can always put out this lambda, and it doesn't affect the answers. So it turns out that it corresponds to our projective plane, because for us, it's the same thing, x and lambda x. Okay, now a smooth elliptic curve is a specific case of such variety which is defined by a unique homogeneous polynomial. So what is an elliptic curve? A smooth elliptic curve, okay, C defined over our projective plane. No projective plane. We take the projective plane, yes, but not over R, but over our finite field. Which is the same thing, is taking F3 without the zero divided up to scalar multiplications. So an elliptic curve C, okay, defined over the projective field, the projective plane, okay, is given by the homogeneous polynomial, okay, which is the following one. This is the most general. So usually when we talk about coordinates in a projective plane or projective space, we use great or capital letters. Okay, so y square z is equal to x in the power of 3 plus little x z2 plus b z3. So you can see that first it is a polynomial, a homogeneous polynomial of order 3, 3, 3, 3, and 3. Now AB can be anything, but such that BA3 plus 27B squared is not 0 in this field. Why? Okay, you will see that this, I mean, usually cryptographer that use elliptic curves, okay, so they use the affine version, which we're going to see in a second, but they don't really understand why do we need in this condition. So, but if you look at the projective origin, then you can understand why. Because you want this projective curve to be smooth, okay? And if you have the gradient be the zero vector somewhere, so it doesn't admit at that point a tangent, okay? So if this can be defined no, so here it's not given by a homogeneous polynomial, given by just this, like, okay. But this can be defined using a homogeneous polynomial, because this is an equation. This is not a polynomial. This is an equation. But this can be defined using a homogeneous polynomial. Which is the following one. Is so this C is actually f x y z equals to 0. This is how we define in the most general way surfaces. Because if we are dealing at some three-dimensional space and we have one polynomial, so this variety is two-dimensional. Okay, so this is a way to define a surface. But we want this surface to be smooth. So we don't want the gradient to be of vector 0, 0, 0 because it's not a vector. I mean, it's a vector, it doesn't have any direction. So we don't want the gradient. What is the gradient? Okay, is in white the now I take the derivation with respect to z. Now we don't want this to be a zero vector at some point. So if we move the point this point, okay, and then we can divide. I mean, once we remove this point, we can assume that that the z is not zero, because the only way z is zero is in this way. Okay, because if z is zero, look at this equation. Okay, if z is zero, okay, so this is also zero, so x must be also zero. So the only point on which z is zero is this point. Remember that 0, 1, 0 is like 0, 2, 0, etc. So when we remove this point, then 0 is not z is not 0 anymore, and we can divide by z. You see how? I mean, we find this called affine. This is the usual coordinates. The usual coordinates means that little x is x divided by z, and little y is y divided by z. So once we divide by z, we get that. So C in the affine form, and this is maybe the starting point of many cryptographers, okay, is y square. You see, I'm dividing by z in the power of 3. Okay, so here I get y square. Okay, y square equal to x third, because I divided this in Z3. Maybe yeah, it would be better if I just take it. So if I divide by Z in the power of 3, and I can divide because I remove the point in which Z is 0, so I get this form of y squared is x in the power of 3 plus x little x plus just b. So this is the affine elliptic curve. As you see, it's not an homogeneous space anymore. Okay, so where did we start? We started by an homogeneous polynomial here. Okay, and we had this condition. Why do we had this condition? First, we have to say, I didn't say it, that the character of FQ, the character of Q is just the prime number from which we started.
I have a question.
Yes.
The affine coordinate of y shouldn't be y times z instead of dividing y by
What is
z?
what? Sorry.
Y multiplication of y by z.
Where?
Since below, you said that y equals to big Y, to capital Y, divided by z, but it doesn't add up with the what you wrote. If you write it,
why?
because y capital Y square, yes, so it's y square divided by z square. Okay, I think it works.
Okay.
Okay, I'll think about it some more.
Okay. Okay. So now we want to understand what is how do we use this? Okay, and why did we have chosen this kind of equation? Okay, so the answer is the following. Okay, I mean, let us remember what we want to do. We want to have some group structure. A group structure means that we have two inputs, say P and Q, and one output from the same kind. This is a group structure, G. So what is the group action or structure here? Okay, we look at I mean, over R, it looks like this. I mean, such an equation looks in general like this. Something like this. Why it looks like this? Because y is plus minus the square. I mean, it's the same thing. I mean, this is a symmetric ray. Okay. And since it's of degree 3, any line goes through maximum 3 points. So we want to create such a machinery. Okay, so what do we do? We take an element here, P. I mean, this belongs to the elliptic curve because it's on the graph. And we take another point, for example, here, Q. Or I would say just to make it a little and now we take the line that goes through the both. I mean, there's only one such line. And we get to the third intersection. Now, P plus Q, this is the operation of the group. We call it plus. Okay, we don't take it as this point, but rather on this reflection. I mean, we take the same X, but minus R. It's here. Okay. This is how we add 2 points over the curve. Okay. Why we take the reflection, I will explain. Okay. But just from now, I just want to describe the group operation. Now, if I take 2 points which are the same, for example, P plus P. Okay, for example, here, this is P. So P plus P becomes a tangent line. So this will be the intersection. So again, we take the reflection. And this will be 2P. So we have actually 2 kinds of addition. If these are 2 different points, then we take the intersection reflection. And if it's the same point, I mean, it's the same thing actually. That because it's getting closer and closer until it becomes the tangent. So again, P plus P, it's here, 2P. And why do we do reflection? What is the neutral element here? The neutral element here, okay, will be the point at infinity, which we have just removed, because the projective space contains another point, which is infinity, which is the pole. I mean, which does not exist when we look at the plane. Okay, and this point will be considered as the neutral element. So P plus O. O is a point in an infinity. Should be equal to P. So what is the point in infinity? For example, you take this P. Okay. So you look at the line that is horizontal. This is O. O is here, is always in an infinity. So what will be, so P plus O should be still P. But if we think about the machinery that we have just described, then we should have taken the intersection and then the reflection, so it goes back to P. Okay, this is the reflection of the third point. Again, on the line. Okay, on the horizontal line. Okay, so this is why we take the reflection in order to have this. Okay, so P plus O, we take the horizontal line. We should have arrived to this interaction, but we take the reflection, which is again P. So from now you see that any inverse of P, if P is for example, if P is XP YP, so minus P will be the same XP but with minus P. Okay, this is minus P, because P plus minus P. Okay, so the third point on the line is O. So P minus P is O. Okay, this is the way we do in elliptic curves. Okay, now how does it have to do with cryptography? So the answer is now you look at this. This is very nice over R. But if we take it over FQ, the points here are not being drawn the same, because it's all modulo some P or some Q if it's extended field, say over P. So so this curve over FP becomes many points. So in order to I mean, you okay, so in elliptic in cryptography, one takes the group G to be generated by some point P. Now P is public, and anyone knows what is P. Okay, but we don't know what is a private key. So this is public for everyone. A public key, or I would say individual public key, is actually a NP, or if it's Alice, so say AP. A is some number in FP. But once you know that, you don't know, hey, A is private. So it's the same thing all the time. It's the same discrete log problem, because in the additive way we write AP, but it's exactly like writing P in the power of A. So we write it this way because it's like addition. But once you know that, okay, you don't know that this remains private. Now, everyone knows the generator P. So AP is another point here, somewhere, and this is public. So you could have started by P and do P plus P is this. Now this plus P is another point. After that, that point with P is another point, and goes like this in some iterative way until you get this AP, and the number of steps you needed would be A. But it's too hard. It's too hard. I mean, the complexity is too strong. Okay. So once we know AP, we don't know A. And from now on, all the things that we have seen can be implemented over this machinery. Let me show you. Okay, how does it look like? So you see here, they begin with the affine elliptic curve, and we call the point infinity just infinity. Okay. I don't see they begin with the projective description. Now I want to show you how does it look like. They don't show us. I want to show you some picture. Okay, just a minute. Just a minute. Maybe they show it this way. Okay, this is an elliptic curve, and what you see here on the right, okay, is over R. But how does it look over a finite field? You see here are different choices of little a and little b. For example, in the picture of 1, the a is -1 and b is 0. And the most right one, the a is -1 and the b is 1. So you see you get different elliptic, but this is known, the choice of the elliptic curve. What is not known, I mean, it's the private key. So next time we will talk about how do we find explicitly. You see these coordinates of the addition. But I want to show you how does it look over a finite field. They don't show us. How does it look over a finite field? Oh, yeah. You see, now this is the curve. This is the rational point. What you see here, this is the rational points of the elliptic curve over a prime field F61. Now you see, I mean, I don't know how you say balagan. You don't understand anything here. I mean, okay. Because once you do it modulo, then all these points have no rule, okay? And this kind of cryptography is much stronger than going over a prime field, because you can not attack here with the number sieve that we have seen last time, okay? And this is very hard to compute. I mean, many steps. I mean, you must go step after step. You know P, then you know what 2P, and then 3P, and etc. Okay, so this is the thing. So next time we will see how to compute the coordinates of these points. I mean, once we have add P to Q, so how to compute the coordinate of R of their sum? Okay, you just have to take the line and compute these coordinates. You see that they are doing it where? Here. Here. You see, this is S. This is S is the Shipua. Is the I don't know if you say it.
Slope, I think.
So sorry?
I think slope. I may be mistaken. Slope.
What?
Slope, maybe.
Slope. Okay, but
Maybe.
we okay. Until next time, I will see how do you call it. I mean, it's that just delta y divided by just delta x of the line. I mean, in the line you have the coefficient of x and the coefficient of y. So this is the coefficient of x. Okay. In B you have A and B. So this is A. Okay. So okay. So we're gonna see it next time. But now, why did we took the power of 3 in the equation? I mean, in the polynomial. The reason is that we wanted 3 points to be on the line, because we wanted to have the binary system that you can put 2 points and have the third one. The third one you will get because the curve is of order 3. But if we have been using some greater power, then it wouldn't be a binary system anymore. Okay. So this is what we call elliptic curve cryptography. Okay. So you have any a question? Now, of course, it's an abelian group, because it doesn't matter if you take P plus Q or Q plus P. I mean, it's the same line. And once you choose a specific point, then of course, all being generated by this point, it's not only abelian, it's also cyclic, because this is the way you constructed your group by all the powers of a specific point. I mean, powers, we don't write it as a power, we write it as an addition in AP, okay? So once it is a cyclic group, so again, you can use the DLP, the Diffie-Hellman, the same thing, but now not over a field, but over something more complicated, which is an elliptic curve.
In order to decode, I need to go, if I have A and I see AP, so I need to go the reverse way 8 times, right? So I need
You're
to
right,
compute.
exactly.
It doesn't take too much time.
This is why today elliptic curves, it's about 80% of the market.
No, but if I want to communicate with you, so it will take too much time to.
No, we don't do that. It's just like in the Diffie-Hellman. We know PA. I mean, I send to you AP. It's like P in the power of A. And I have my own B. I know my B. So the mutual key will be just multiplied by B. You see what I mean?
Yeah, so it is just another representation of the same,
Yes.
I don't know, like same material. It's like,
Yes, yes, but here is more complicated. So we will talk about it more next week, which will be actually the last meeting before the test. So if we call it test, I don't know, presentation. Okay. So thank you for listening, and see you next week.
okay, thank you.
Thank you.
Bye.